it is my pleasure to announce. It is my pleasure to announce today's speaker, Gennadiy Navrotskiy, with the talk about weighted number of planar vector random vector fields. Please, Gennadiy.
Yes. Yes, can you see my screen?
Yes, yes, we see your screen. It's better to switch to the demonstration mode. Okay, it's good now. Please.
Thank you. So this talk is devoted to certain construction of a smooth random knot and its properties, namely to some topological properties of this knot and its and the connection to its winding number. So let us begin with some necessary definition. So a knot in the space in the three-dimensional space is closed smooth curve without self-intersections. And two knots are considered equivalent if they can be transformed into one another by some bijective orientation preserving infinity differentiable mapping. So yes, in order to distinguish two knots, we have the function of knots that take the same values on homotopic nodes. Yes. So in order to distinguish two non-homotopic nodes, we can find a knot invariant that can that take different values on these two nodes. There is a full complete system of knot invariants, which means that for any two non-homotopic nodes, there is an invariant in this system that distinguishes them. This so-called system of Vassiljev invariants. Yes. Yes. Further, we will consider one example of a knot invariant and its connection to a winding number. So, in the paper "Stationary Random Knot" by Andrei Anatolyevich Drugovtsev, there was proposed a following way of constructing a smooth random knot. Let us consider a random field on R2 with values in R3. That is a centered Gaussian random field with dependent identically distributed coordinates. Since its covariance function is infinity differentiable, the field Xi has infinity differentiable modification. So, further, so now we can proceed to constructing our random knot. So for that, we consider B, which is the image of a unit circle in 3 under the mapping psi. So in order for beta to be a random node, it needs to have no points of self-intersection, which will was points, so it is, beta is indeed a random node. So other it occurs and was also proved by Dorogovtsev that for any smooth curve without self-intersection NS3, beta can be homotopic to this curve with positive probability. So beta with with positive probability, beta can have arbitrary topological type. And further, beta can have arbitrary complexities. What we mean by what we mean by complexity of the node, we will explain further. Yes. So now let us define the winding number. The winding number gamma of psi and L of some continuous planar vector field along a continuous curve is just the increment of the angular function divided by 2 pi. So it's just the number of rotations of the vector from origin to to psi. Yes, so it is here we have a parameterization A01, but it is obvious that we can take any interval AB, and it is important that psi does not take zero values on this curve. Okay. Then, further, now let us consider the connection between winding number and the number of up crossings and down crossings of one of its component. In our case, it's X component, conditioned on the fact that Y component is positive. So this, we can see that if we have one rotation. Here then the X component takes value 0, and X component is decreasing at point 0, and if vice versa, if X component is increasing at point 0, then we would have a full rotation in the negative direction. So the number of down crossings by the one component corresponds to the number of positive of rotations in positive direction, and number of up crossings of X coordinate corresponds to the number of negative rotations. So further, let us consider one example of a node invariant. So on each projection, or node on the plane, we can consider the number of overpasses, where overpass is sub-arc of the node that never goes under a crossing. So, and maximal overpass is pass that could not be made any longer. So if we consider here on the image we have an example of projection of the node. So we have here a plane z equals 0, and we consider if we consider the projection of the node on the orthogonal plane, which is the plane xy, that we can see then if we have any if we have a rotation, a positive rotation, then we have at least one maximal overpass. Yes, so and if we have rotation in the negative direction, then we also have at least one maximum overpass. So it follows that the absolute value of absolute value of the Winding number by a radius vector of our node is greater or equal than it's lesser or equal than the bridge number. Yes, and here we consider since we consider here bridge number over the plane z. So we consider the node in the orthogonal plane. That's why we take only two components, x and y, our field, and look at the Winding number. So further, we have the following way to calculate the Winding number of a continuous vector field on the boundary of some region. So, well, in other words, if our vector field has some k, let's say k zeros inside the region B, then the Winding number on the boundary of B is just equal to the sum of Winding numbers of psi on the small enough circles with centers at those zeros. Well, small enough, it means that the circle does not contain any other zeros of the field psi. Yes, then it is also important that field psi is continuous. It does not have any other critical points. Yes, any other critical points except for zeros. So if psi is continuously differentiable at point u, and if its matrix of partial derivatives is non-degenerate, then index is just sign of determinant of this matrix partial derivatives. So we can then calculate the Winding number are just the sum of signs of determinants in these points. Yes. So yes. So, and we want to apply the index formula to our random field xi, and to this projection of our node beta on the plane xy. Yes. So for that, we also need to prove that we don't have other critical points except for zeros. Yes, well, that we know because we know that our field is infinitely differentiable, and we also need to prove that the field psi all zeros, the matrix of partial derivatives in any 0 point on B is non-degenerate, which means its determinant does not equal 0. So that was proved, and we discussed it. Yes, we discussed it previous time, and we also discussed that the field psi with probability 1 has only a finite number of zeros on any bounded region. So then we can use the index formula. Or in a way, if we just take n plus denotes the number of such points in B that xi tends to 0, and the matrix of partial derivatives has positive determinant, and in minus vice versa, when it has negative determinant, then we can represent the winning number of psi along the boundary of the region B as just their difference. Yes, so our goal was to find energy deviation principle for the winning number, and it occurs that the probability of large deviation is connected to asymptotics of higher order moments of a random variable, but well, since it's asymptotics for the higher order moment of windy number is well complex, we did not establish yes, we did not establish a large deviation principle. Yes. So then, but we obtained well a formula for calculation of factorial moments of VD number of the random field. So first we will use a formula that was obtained in the book by Adler Taylor, which permits calculation of the expectation of number of points in which a random vector field takes values from set B from Rk, and which Ft equals takes some fixed value U in Rn. Yes, so and what's important about this formula is that it requires existence of non-degenerate density for non-degenerate density of the joint distribution of Ft, nabla Ft, and G of T. These three random fields. So, yes, and in our case, since we want to calculate the number of points in which a determinant takes yes, number of points where this determinant takes positive or negative values. Well, it won't be non-degenerate. Well, since the determinant of number xi and number xi are dependent. So Kuznetsov proved the modification of this lemma, also called yes, the modification of this result by Adler and Taylor, also called expectation method theorem. So he found conditions under which we can calculate the variance and expectation for the winding number of random field F along some piecewise smooth closed curve gamma. Yes. So what's important here it is well that we need to have conditional densities for both x for both f conditioned on number f of t and for well number f of t conditioned on f of t. We also need that this field its derivative and all its components have bounded moments of the order 4, and we needed a condition on the modulus of continuity also of the order 4. So yes, then if all these conditions hold, then we have yes the following formula for the expectation of the winding number of the field F on the boundary of region T, and for the yes, and for the second moment of this winding number. Yes. So then y yes. So further, what we will try to do is that we will follow these methods in order to find higher order factorial moments of the winding number. So we can define the factorial powers of a random variable, just any number, and then we have yes, factorial moments is just expectation of factorial power. So then we have modification, yes, further modification of expectation meta theorem that we obtained. So here we need bounded moments of the order 2k, and we also need, in this case, we introduce a new random field and a new region B0, which is b to the power k, where k is the order of factorial moments that we want to calculate. So then and b0 is just bk, but without a diagonal, which means that all of its points are pairwise different. Oh yes. So then further here it is similar. Yes, the order conditions are similar to expectation meta theorem, in which means that we also need to have conditional probability density for both f tilde and nabla f tilde, and we also need the modulus of continuity to be order 2k. Oh. Yes, so where do we? So where do we get the order 2k? So we have we then obtain the following formula for this higher order factorial moments. Which is, yes, we have now an expression for the integral, this expectation through the factorial moments. So then what is the idea of the proof? So first, let us define just two sets, which is set D1, set of all matrices 2 times 2 with positive determinant and with negative determinant, and then we define a new vector field on B0, which is just nabla of F, but on B0, so we have all R I to be pairwise different. So then we can fix a vector of S1 Sk and delta greater than 0 and consider the following sets, which is yes, T1, Tk, but all of them are, well, difference between all Ty, Tj is greater or equal than delta if I does not equal j. And then we can we also consider the numbers of all t of n k delta, which is just the number of such points t tilde in bk delta, such that the matrix of derivative is positive or negative in point tj, and the field f turns to 0. Then we use for these fields f tilde j tilde and sets b k delta, bk delta, and sets the product of sets dsj. We can apply the expectation meta theorem that we discussed earlier. So then what do we obtain? Is this. So here we have just the absolute value of determinant number of R, but since we have here we know that the signs of components number f tilde r tilde, then we can just remove the absolute value and just write this one. Sk. So, and then we can pass to data goes to 0. then this integral will just converge to b to integral over b k, and these sets will just yes. So this well, what happens to this set when we pass to delta to 0, then we have t tilde, but they now from B0, so they just are all pairwise different. Yes. So, and since this convergence of the number of points is monotonic nodes, then we can pass to the limit, and then what we have? We have here the number of points in BK. So let's say we have all SEI equal to +1. Then we just have here the number of points of in BK in B0 such that yes in BK such that pairwise coordinates are all different, and f in these points equals to 0, and number f belongs to yes, and determinant of this matrix number f is positive. So how many? Well, we know then that it will be this number will be just equal to n plus times times 1 plus minus k plus. So it is, if we consider all vectors of the length k. So yes, so if we so then we pass to the limit, and we obtain this formula that we yes, that we are discussing. Then yes. So then further it may be difficult to check the conditions on the modulus of continuity, but for Gaussian case, this condition has a more simple form, which was verified by Kuznetsov. So if H is standard Gaussian random field, it is sufficient that its covariance function would be twice continuously differentiable, and then we know that its modulus of continuity would be well, would satisfy our condition E, which is here. So we need for all k, but it's yes. So this condition is already satisfied for all Gaussian random fields with twice differentiable covariance function. So further, yes. Also, we have already expectation of factorial moments theorem. That was proved by Adler-Taylor. but in their case, once again, it was required that all that for any points t from t, the joint distribution of f, nabla f, and g would be non-degenerate, and well, this condition in our case wasn't satisfied, so we had to modify. So and further, what we will further we would like to introduce some mixing condition with, and also show some mixing conditions, and also show a central limit theorem. So first, well, what is well, alpha mixing, the condition, and rho mixing. So for rho mixing, it is just supreme of covariance where x, y are some random variables such that they are square integrable and measurable with respect to A, to sigma algebra A and B respectively. And norm x and y is, well, is not greater than 1. And further, we can introduce mixing coefficients for some random fields on the matrix space. So yes, yes, and we can introduce so-called mixing random fields. So field is mixing if its mixing coefficient converges to 0. Distance, well, k converges to infinity. Yes, and here C can mean respectively alpha mixing coefficient or rho mixing coefficient. Yes. So further, we will consider the following central limit theorem that was proved by Bolthausen in 1982. So he considered lambda n, which is sequence of subsets in zeta d. So in this paper, it was considered, yes, in Bolthausen's paper, where the random fields on zeta to the power d were considered. So, and if lambda n sequence of subsets of the d that satisfy such conditions, and also we define sum of Sn for our for the random field x, which is also a random field on zeta to the power d, then the following yes, then if the following condition holds for their mixing coefficients, then we can conclude that there is a central limit theorem for the sums of this random field, over the values of this random field over lambda n. Yes. In our case, we will try to use it for the following random field. So let us take f, which is from 2 to r, and which is a periodic function. on the plane with period 1. So we can define xk a, which are integrals over the square k plus 1 times a plus 1. So it is just the sum over all zeros rows of a random field psi. So since f of u is non, yes, f of u is deterministic function, then this O just just is measurable back to sigma psi u, and u from k k plus 1 times a plus more, and since our random field yes, since random field psi is stationary, then xk is also stationary. Yes, and since f is also, well, f is also a periodic function, then yes. So then we consider the following. Yes, we just consider squares on the plane zeta 2, and we will calculate sums over values of x r, where r from these squares. So we know from the Kolmogorov, from the theorem proved by Kolmogorov and Rozanov, that for Gaussian random stationary fields, the alpha mixing and rho mixing are equivalent, and then we get the estimate that the alpha mixing coefficient is just not yes, just bounded by some constant on the maximum of covariance, which is e to the power minus m squared. Then we see that well, this sum converges, and then what we need also to prove is that the third moment is exists, it is finite, but we will know that third moment is bounded by a constant times expectation of number of 0 points cubed. So, and we know well how to calculate it. Yes, you know how to calculate it using yes, factorial moments, and factorial moments are finite. So we conclude that third moment is also finite, and yes, and therefore we conclude that the conditions of the theorem for convergence hold, and therefore yes, the conclusion is that Sn divided by sigma converges to converges in distribution to a standard normal variable. So that's all, I think.
Okay. Thank you very much for interesting talk. And maybe someone have questions or comments, please.
I have already asked this question. So, how essential the concrete form of the covariance of Xi?
Essential to what? Essential for existence of factorial moments, or what? Well, for factorial moments, we just need these conditions. So it's not for Xi. So, and we also have this condition holds for all Gaussian random fields with twice differentiable covariance functions.
Okay, thanks.
Okay, other questions, comments, please?
And what about exponential moments of this n capital?
Maybe let me say a few words about this. It occurs that even for a number of approaches, if we don't move the level under which we are calculating approaches, then there are no a lot of information about its distribution. So we don't know about exponential moments. Of course, we will continue to try using the obtained formula for the factorial moments to do something. The first idea was to get large deviations, but we was not succeed because of complexity of the expressions for factorial moments. So at the moment we don't know. Other questions, please? Okay, let me make a final comment. The problem here is that we really discussing the knot, and we want to have the distribution of its characteristics. It is not a problem related to asymptotic when we move the level somewhere or discussing the level sets for Gaussian fields when the level tends to infinity. So if we don't move the level, if we consider just fixed plane which cut our knot, then it's gonna be a problem, and we just want to have more information about the distribution of Widen numbers and other corresponding topological characteristics. Okay, so Gennadiy, thank you again. for interesting talk, and maybe Katerina, do you remember who will be the next speaker?
The next speaker, Kirill Kuchinsky.
Okay. Good. So for today, that's all. See you next week. Bye.
Thank you. Bye.